The way we power our world is changing. We are approaching the tipping point to a green future where most of our energy comes from sustainable, renewable sources. South Australia is one of the world leaders in this transformation. The last coal generator here closed in May 2016 as financial and environmental pressures mounted up. Much of this financial pressure can be attributed to the increasing penetration of wind and rooftop solar generation in the state. Unfortunately, the power system was designed around these large central fossil fuel burning generators. Grid stability was maintained by the large rotating masses within these generators, which reacted slowly to change, providing excellent fault ride-through capability. This is in stark contrast to the behaviour of solar and wind generators. These generators are intermittent, that is, they only generate power when the sun is shining or the wind is blowing. We don't have that fine control over output that we had with fossil fuel generators. We can't just add more coal to the hopper anymore. This is where energy storage comes into the story. Just like a farmer makes hay when the sun shines, if we can store excess energy while demand is low and the generating conditions are good, we could conceivably power the world without the need for burning our finite resources. The most commercially advanced forms of energy storage at the moment are electrochemical batteries and pumped hydro storage. We are all familiar with electrochemical batteries. They power our phones, cars, appliances, and so on. They are capable of providing reasonably large storage capacity and very fast charge and discharge rates. Pumped hydro, on the other hand, is simply pumping water up to a reservoir, storing energy as gravitational potential energy. This method is capable of storing enormous amounts of energy, but the rate of storage is much slower than batteries. So we have the technology to generate power and store the excess, which would allow us to provide all our energy needs in a sustainable, renewable and environmentally responsible way. But this then begs the question, how much storage do we need in a generator in the state of South Australia? What about in Australia? How about the whole world? During this project, we aim to develop the techniques to answer the first two questions and provide a basis to answer the third and further. Answering questions like this is not trivial. Sure, you could just say, let's build enough storage to power the state for a year, but that is not realistic. The ideal solution is to have enough energy storage, but not so much that we're being wasteful with our finite resources. Another question we had to answer was how to quantify a battery's effect. After all, without knowing what it does, how can we say how much we need? Conveniently, we had an excellent case study come up. The Hornsdale wind farm was about to install the world's largest lithium-ion battery, rated 100 megawatt output and 129 megawatt hours of capacity. We set about determining how the battery can be used to reduce the intermittency of this wind generator, as this would result in the generator behaving similarly to those fossil fuel generators we want to replace. We used a bespoke genetic algorithm and a year's worth of generation data to model how much the variance of the output could be reduced. This algorithm looped through 3-day data windows, searching over 200,000 possible solutions for each to find the near optimal solution, and resulted in a reduction in variance of nearly 40%. With this information, we were able to say that the algorithm worked, and so we looked to flip the problem around and see how much storage we would need to achieve the sum target of variance reduction. We ran the model again for different battery capacities and found that reducing the variance of the approximately 300 megawatt Hornsdale site by 70% would take 500 megawatt hours of stored energy. After this, we quickly modified the model to run on a generation data for the whole state and found that a 70% reduction in variance required approximately 3.5 gigawatt hours of energy storage. While it is promising to see that our algorithm works and that batteries can be used to effectively reduce generator intermittency, it remains to be seen how much variance reduction is actually needed for a stable grid. The next phase of this project could work on this aspect, expand to include the whole NEM, or improve the model to include more non-ideal behaviours, amongst many other possibilities. Besides the Tesla battery, several other energy storage systems were announced for development during the course of this project, including a 30 megawatt system in Dalrymple and another 100 megawatts of battery and 600 megawatt hour of pumped hydro in Whyalla. So it's safe to say that energy storage systems are going to play a major role in our energy systems in the future.